Imagine something smaller than anything you've ever seen. Inside it are forces so powerful, they hold the universe together. Nuclear physics isn't just about power plants or weapons. It's about the invisible engine inside every atom, the thing that makes stars burn and matter exist. Every atom has a tiny center called the nucleus. Inside the nucleus are protons, which carry a positive charge, and neutrons, which carry no charge at all. Surrounding the nucleus are electrons, which are negatively charged. Now, here's where things get interesting. Protons are positively charged. Positive charges repel each other. If you try to push two magnets together on the same side, they push apart. So why doesn't the nucleus fly apart? Because of something called the strong nuclear force. This force is one of the four fundamental forces of nature, and at very short distances, it's the strongest one we know of. It acts like an incredibly powerful glue that binds protons and neutrons together, but it only works at extremely tiny distances, about the size of the nucleus itself. Outside that range, it disappears. This balance between electrical repulsion and the strong force determines whether a nucleus is stable. Not all nuclei are stable. If there are too many protons, the electrical repulsion becomes overwhelming. If there are too many or too few neutrons, the balance is disrupted. Neutrons help stabilize the nucleus by adding strong force attraction without adding extra electric repulsion. Atoms that have the same number of protons but different numbers of neutrons are called isotopes. Some isotopes are stable, others are unstable. Unstable nuclei try to fix themselves, and when they do, they release radiation. This process is called radioactive decay. There are three main types. In alpha decay, the nucleus ejects two protons and two neutrons bundled together. This reduces its size and lowers the internal repulsion. In beta decay, a neutron transforms into a proton and releases an electron. This actually changes the element into a different one. In gamma decay, the nucleus releases excess energy in the form of high-energy light. No particles leave, just energy. One important thing to understand is that decay is random. You cannot predict when a single atom will decay. But if you look at a large group of atoms, patterns emerge. This is where the idea of half-life comes in. A half-life is the amount of time it takes for half of a radioactive sample to decay. Not all of it, just half. After another half-life, half of what remains decays again. It's a statistical rule, not a countdown clock inside each atom. Now, let's talk about energy. When nuclei change, whether through decay or through reactions, energy can be released. That's because a tiny amount of mass is converted into energy. Einstein described this with the equation E equals mc squared. Even a very small amount of mass multiplied by the speed of light squared becomes an enormous amount of energy. There are two major nuclear reactions that release this energy: fission and fusion. In fission, a heavy nucleus splits into smaller nuclei. This releases energy and sometimes additional neutrons, which can trigger more fission events. This chain reaction is what powers nuclear reactors and atomic bombs. In fusion, light nuclei combine to form a heavier nucleus. This also releases energy, and it's the process that powers the sun and other stars. Fusion produces even more energy than fission, but it requires extreme heat and pressure to overcome the natural repulsion between positively charged nuclei. Inside, every atom is a balance of forces so powerful they shape the cosmos. Nuclear physics explains why stars shine, why some elements are radioactive, and how matter itself is structured at its most fundamental level. It's happening everywhere, all the time. Inside stars, inside reactors, and even in trace amounts inside your own body. The universe isn't just vast, it's intense at the smallest scales, and that's nuclear physics. Simple in concept, but powerful beyond imagination. If you found this interesting, consider subscribing for more deep dives into the science shaping our future.